about something I love so much. So, there's always a question, where do you read about this stuff? Where do you learn about this stuff? There's actually the best textbook in the world about this stuff. It's called the Green Book. It's Doug Ravenel's Complex Cobordism and Stable Homotopy Groups of Spheres. And certainly a lot of the stuff that I'm going to talk about today, I probably learned more or less in one form or another from this book when I was a graduate student. So we're talking about homotopy groups of spheres. Oh, I hope these are going to be relatively legible. That looks kind of. Can you guys see that? Somewhat. It's a bit small. How about if I? Oh, you can't see the numbers. Is that a little better? Okay. Anyway, the numbers aren't going to matter so much, except whether it is a number or not. So we're talking about the homotopy groups of spheres, and so this is a chart showing pi I of Sn, and so you see I runs off the top and it's running on the y-axis, and so these things, what do we observe from this chart? Oops, I see how I have to do this. Okay, so firstly, I'll try and help you guys out when I can by zooming in. Oh, shoot, and there's another problem where the chart isn't displaying my highlighting. I hope this isn't. Oh, okay. Anyway, I'll try and we're missing my highlighting, but anyway. What I tried to highlight on the slide but didn't show up on this projector is that the lower homotopy groups of spheres are, of course, all 0. Then you look along this diagonal here and you see all these z's, and so that's reflective of the fact that pi k of sk is z, given by the degree map. And the higher homotopy groups of spheres are, well, they're very complicated and very mysterious. Oh, I see. I have to do this. Okay. Now, and again, I apologize. My highlighting just simply isn't showing up. So I'll just try and point to everything. So the infinite subgroups, that is, if you take the homotopy groups of spheres and tensor them with Q, these were completely determined by Sayre in the 50s. And not only do you have pi k of sk having these factors of z, but you'll also see factors of z over here, and here's one over here, and here's one over here. In general, you're going to see these things. See here. In general, you're going to see these things in pi 4n minus 1 of S2n. There's a map from these groups to Z, which is the Hopf invariant. And let me just remind you how this map is defined. So if you have an element alpha in here, you take its cofiber, and that's a two-cell complex. So you got a cell in dimension 2n and a cell in dimension 4n. And then you look at cohomology, and you've got a z in dimension 2n, you've got a z in dimension 4n. Let's call this generator x and this generator y. And then x squared is equal to plus or minus the Hopf invariant of alpha times y. And so what we're saying here is that this map, this Hopf invariant map, is non-trivial in these dimensions. But that doesn't mean that it is injective or surjective. And so the surjectivity amounts to the question of whether you have a Hopf invariant 1 element. So you ask, when can you have a Hopf invariant 1 element? Well, an example of a Hopf invariant 1 element is the Hopf map, the map from S3, the Hopf vibration from S3 to S2. And how is this map defined? Well, we think about S3 as being the unit sphere in C2 minus the origin. And then we mod out by C cross action to go to CP1, which is otherwise known as S2, and this map is eta. This is your Hopf invariant 1 map. Well, so this is a construction using the complex numbers, but I could have equally well used the real numbers, and then this would have given me a map from S1 to S1, and this would be a degree 2 map from S1 to S1. Or I could use the Hamiltonians. Can you guys see down here, or is this thing blocking you? Okay. I don't. So you've got, huh? Can you move it? Yeah, I think I'm not going to touch it. Let me just move somewhere else. How about that? So then you've got associated to the Hamiltonians, you have a map from S7 to S4, and this guy's name is nu, Hopf Invariant 1 element. And using the octonians, you get a map from S15 to S8, and this guy's name is sigma. And then Adams, in 1960 paper, showed that these are the only dimensions where there are Hopf Invariant 1 elements. These only what I mean by this is the difference between these two numbers, those dimensions. So I'll talk about that in a second when I talk about stable stems. Okay, so if you look along the diagonals, of course, the Freudenthal suspension theorem implies that if you look along these diagonals, then the values eventually stabilize to give you the same values. And so those stable values are the stable homotopy groups of spheres. So this stable value along this diagonal is pi 0, along this diagonal is pi 1, along this diagonal is pi 2, etc. So you take the limit of pi n plus k of sk. Well, now, with the exception of pi 0, these are all finite abelian groups. And so then they decompose as a direct sum of their p torsion over all the primes. And so therefore, I can study these stable homotopy groups by working one prime at a time. And that's typically what's done. This is a picture of the known stable homotopy groups of spheres, just the two component of the stable homotopy groups of spheres. Is this one a little easier for you guys to read? Okay, good. So anyway, in this picture, each one of these dots represents a factor of z mod 2, and the columns have the answer. So each dot, well, the vertical lines between the dots indicate additive extensions between these z mod 2s. So for instance, if you look in pi 3 here, these three z mod 2s are joined by vertical lines. So that means the three z mod 2s make a z mod 8. So the two component of pi 3 is z mod 8. Whereas if you look at pi 8, the two component of that, well, I've got two dots here, but they're not joined by vertical lines. And so it's a z mod 2 direct sum z mod 2. And in this picture, the vertical arrangement of the dots is arbitrary, but it's done in a manner to suggest patterns. And oh, good, that showed up. This is going to be real bad if none of this showed up. Okay, but I know why it showed up too. Okay, thanks. Yeah, so it's not going to. There'll still be problems later on. So here I've highlighted one particular pattern. So you see this very regular pattern down at the bottom with roughly 8-fold periodicity, and this is the image of the J homomorphism. So what's the J homomorphism? Well, so there's a map from SON to loops NSN, which is obtained if I have a matrix viewed as a map from Rn to Rn, and then I set it to the one-point compactification of that map. So that'll be a map from Sn to Sn. And so I could take the limit of these maps as n goes to infinity, and that gives me a map from the infinite special orthogonal group to QS0, the loops infinity of sigma infinity of the zero sphere. And then I could apply homotopy groups to this map. And then the homotopy groups of QS0 are the stable homotopy groups of spheres. And this map is called the J homomorphism. The reason why this homomorphism is so interesting is because the homotopy groups of SO were computed by Bott as part of his famous Bott periodicity theorem. And they were shown to have an 8-fold periodicity that's reflected in the roughly 8-fold periodicity you see up here. So these groups here are in pi 1, it's Z2, 0, Z, 0, 0, 0, Z, Z2, Z2, 0, Z, 0, 0, 0, Z, etc., with the 8-fold periodicity. Now, the image of this map is known. So Adams, in 1966 paper, J of x4, so the Z mod 2s map in non-trivially. And the Z's, they got to go to some finite cyclic group because the target is finite. And so the real issue is what is their image, or what is the order of the image of J. So the order of the image of J in the dimensions where there's a Z, so that's in dimensions 4k minus 1, is equal to the denominator of the 2kth Bernoulli number over 4k. Now, this Adams didn't actually completely prove this theorem. There was an issue of a factor of 2 that was later resolved related to the Adams conjecture. Yeah. Can I define the Bernoulli number? Yeah. Well, I use whatever convention makes this theorem true. So, for instance, for you, are odd Bernoulli numbers 0? Yeah. So for me too. I suspect we use the same convention. Okay.
If hypothetically there was someone who still after that maybe didn't even know what a Bernoulli number was, is that not going to be a problem?
It's completely not a problem, because I want to advertise to you that whereas this is a very impressive answer involving these fancy Bernoulli numbers, in fact, if you look at the p component for every prime p, it's way easier to understand what the answer is. Okay, so take a look at this picture over here. You see that it's really a question of what the heights of these little towers are, and they depend on the 2 divisibility of that number plus 1. So the 2 divisibility of the 2-adic valuation of 8 is 3, and I have 4 dots. And the 2-adic valuation of 32 is 5, and I have six dots here. So that's the pattern, okay? It's even easier to understand this pattern at odd prime. So here's a picture of the 3 component of the stable homotopy groups of spheres, and you can see the pattern looks just like a ruler, depending upon 3-adic valuation now of the numbers plus 1. And here's a picture of the 5 component. Now, it's okay that you can't really see this chart so well, because I don't really want you to see it so well, except be impressed by how big it is. So this is a computation that goes all the way out through the 1,000 stem, and this was done in the Green Book, actually. Now, these computations represent roughly the known range of these stable homotopy groups. And the image of J is this very regular pattern down here. Okay, so now this leads us to a question: how do we compute these homotopy groups? How were these computations done? Well, back in the day, Sayre used basically Postnikov tower kind of techniques, and then Toda, he used EHP techniques, and let me tell you about the EHP sequence. So Toda computed the unstable homotopy groups of spheres through about the 20 stem, and we don't know so much farther than that even today for unstable homotopy groups completely. So what's the EHP sequence? Well, you take the map from loops n minus 1 of Sn minus 1 to loops n of Sn, This map is the suspension map. So it's written E for suspension. And then the next map is called H. And it goes from loops n Sn to loops n S2n minus 1. And that stands for Hopf Invariant. And, well, let's localize everything now at p equals 2. And then it turns out this is a fiber sequence. And the fiber, so then I could continue the fiber sequence. And so I have loops n minus 1 or loops n plus 1 of S2n minus 1. And this map is called P for Whitehead product. Now, why is H called the Hopf map? Because it's related to the Hopf invariant. If I apply homotopy to H, I get a map from pi 2n minus 1 of Sn to pi 2n minus 1 of S2n minus 1, which is Z. And this map is nothing more than the Hopf invariant. And this map is related to a certain Whitehead product. So that's why it's called the P map. All right, well, so these are some fiber sequences. I can apply homotopy groups to these fiber sequences and get some long exact sequences. And then I can splice these long exact sequences together, and I get a spectral sequence. And that's called the EHP spectral sequence. So the E1 term of this thing looks like the homotopy groups of odd dimensional spheres. And then the thing converges to, well, the homotopy groups of the colimit of the loops n Sn, so that's the stable homotopy groups of spheres. Just the 2 component, but I'm going to stop writing localized at 2. Okay, so I've got a spectral sequence that starts with the unstable homotopy groups of odd dimensional spheres and converges to the stable homotopy groups of spheres. It seems kind of circular. It seems like this is not going to be of any use at all. But in fact, it is. There's a kind of algorithm for using it. Okay, so I want to talk about that next. So here's a picture of the spectral sequence. Oh, you really can't see this. This is a disaster. Oh, this is just terrible.
If you were able to change the resolution of the screen, that it was possible to get the shading, but then the scale was different. But since you're able to zoom, that might work.
Let's see. Let us see.
It take 2 or 3 minutes to get it done.
2 or 3 minutes. Let me try one thing. I'll try one thing. Let's just see. And if we don't like it, then we can always go back. So let's see here. Let us try this. Screen resolution. Let's see here. That is a very low resolution. What if I go to a, I don't know, choose a random resolution. Let's see here. Let's try this. And now, oh, come on, you. There we are. Let's see what it looks like. I don't know. It looks worse to me.
I think what worked yesterday was to go to an even lower resolution.
Oh, I don't have any lower resolutions. Yeah, this is as low as it gets. Okay. So let's go. Let's continue with this thing. All right, it's okay because honestly, the charts that aren't showing up are charts that are sort of more for like some kind of theatrical effect, and so I can kind of wave at them anyway, and you probably wouldn't know the difference. So let me go back to the chart you can't see. Okay, so let's try and view the presentation. All righty, there we are. Okay, so here's a picture of a spectral sequence which you cannot see. So I won't bother to say anything about it. But I just want to point out that if you arrange it such that the rows of this spectral sequence are the homotopy groups of these various odd-dimensional spheres, and the columns are the answer, the stable homotopy groups of spheres, so you've got differentials, which you can barely see. then I can explain this algorithm called the Curtis algorithm for inductively computing homotopy groups of spheres. So the first step is to compute, so this is the 0 column. This computes the 0 stable homotopy group of spheres. And then once you compute this column, the way this thing is indexed is this gives you all of the values in this chart below this jagged green line. Well, then I could try and compute all the differentials from this column to this column, and then that would give me entire information about the 1 stem. And so then that allows me to push what I know a little further, and then I can push this jagged green line below of which I know everything. Then I have to compute differentials from this column to this column, and then once I do that, I will have successfully computed the 2 stem, and that allows me to push my knowledge just a little further. And in this way, you inductively compute all the homotopy groups of spheres. So if this is that easy, why don't we just compute them all? Well, you have to compute the differentials, and the differentials are very mysterious. Okay. Now this is an even more zoomed out chart that you can even not see even more. But you can barely see actually the differentials. See all the sort of faint arrows here? This is supposed to indicate, this is basically the entire Toda range. And so it's basically meant to show you that there are a lot of differentials in this spectral sequence, and it's very confusing. It's not clear how to do it. However, there is a method that was used by Toda and Mahal and others that is very successful for computing differentials that I'd like to tell you about. Toda also combined this method with ingenious use of various structures, such as Whitehead products and composing maps and Toda brackets and whatnot, to sort of eke out the differentials in this range. Anyway, but here's the method I would like to talk about. So take the EHP sequence. I'm gonna go one further. So it's loops n Sn goes to loops n plus 1 Sn plus 1, and then this goes out by the H map to loops n plus 1 S2n plus 1. And it turns out that there are James Hopf maps that map this to another fiber sequence, which is QRPn minus 1 with a disjoint base point, goes to QRPn with a disjoint base point, goes to QSN. And so this is just the fiber sequence you get by applying Q to the co-fiber sequence. RPN minus 1 goes to RPN, and then project off on the top cell. Well, so then this gives you a map of spectral sequences. So the spectral sequence you get from applying homotopy groups to this guy is the EHP spectral sequence, of course. And the map and the spectral sequence you get by applying homotopy groups to the bottom sequences is the Atiyah-Hirzebruch spectral sequence for computing the stable homotopy groups of RP infinity. So you get a map from the EHP spectral sequence. Let me write it this way. You get a map from the EHP spectral sequence to the Atiyah-Hirzebruch spectral sequence of the stable homotopy groups of Sn to the stable homotopy groups of RP infinity. And this map of spectral sequences then preserves differentials so then you can try and take differentials over here and lift them up over here. You might say, well, that's no better. How do I compute differentials in here? Well, differentials in here are much easier. Understanding differentials in the Atiyah-Hirzebruch spectral sequence basically amounts to understanding the attaching maps between the cells in this stable homotopy type. So then you can compute those differentials if you're know about the homotopy type of RP infinity, and then get these more mysterious differentials up here. Now here's a picture of all of the differentials in this spectral sequence that are obtained by lifting from the Atiyah-Hirzebruch spectral sequence. And all I'd like you to get out of this picture you can't really see is that only a few differentials are missing. So this accounts for actually almost all the differentials in this range, just to show you how robust this technique is. I'd also like to mention something.
How far has this actually been carried out? To what stem?
The HP sequence?
Yeah.
At the prime 2, I think roughly through 24 or 26.
Okay.
It really gets harder, and it gets to be the case where like a paper is like a stem kind of thing. Like it starts to really get heavy going, and then you just get tired. So now I just wanted to mention one other thing, which is the notion of Hopf invariant. So if you have an element in the stable homotopy groups of spheres, well, then you can ask in this spectral sequence what detects it in the E1 term. And so a guy that detects you in the E1 term is called the Hopf invariant. So if you have an element in pi, in one of these groups, that will return the actual, classical Hopf invariant. But if you have an element in a more general stem, the Hopf invariant will be some random element in some unstable homotopy group of some odd dimensional sphere. Okay, so that's the notion of Hopf invariant. So yeah, okay. I was going to tell you some Hopf invariants, but you can't see the picture anyway, so let's not worry about it. There's another invariant, though, that I would like to take this opportunity to tell you about, and that's the Mahal invariant. So the thing to observe here is that, well, if you take a look at these differentials in the Atiyah-Hertzsprung spectral sequence for RP infinity, you'll see that something funny is going on. Namely, these D1 differentials are repeated every couple degrees. And then look at these D3 differentials. This pattern here repeats as this pattern over here, and this pattern over here, and this pattern over here. There's a periodicity amongst these differentials. That periodicity is called James periodicity. In general, a certain length, depending on the length of the differential, there's a certain periodicity those differentials have. And so given this periodicity, this allows you to interpolate these differentials to negative values. So, so add in negative cells into RP infinity. Just continue RP infinity to negative degrees. And you get some kind of glorified spectral sequence that goes not just from the direct sum of n greater than or equal to 0 now, but all n in Z of pi star, the stable homotopy groups of the SNs, and this thing converges to the homotopy groups of some version of RP infinity where you now have cells in every integer dimension. So we'll call this RP minus infinity infinity. Well, this was proven by Lin in 1980 to be the same as the -1 sphere. And so this is actually nothing more than the stable homotopy groups of the -1 sphere. Yeah, that's stable. Well, RP minus infinity is only a spectrum, so I don't really know how to. I'll write. Yeah, so is S -1, I suppose. So, whatever. Yes. This is basically the Siegel conjecture in the special case where the group involved is the group Z mod 2. So this was a big theorem. Okay, so this theorem now gives me a spectral sequence that starts with the stable homotopy groups of spheres and converges to the stable homotopy groups of spheres. Another one of these damn circular spectral sequences. And as we know, this spectral sequence has many differentials because we're interpolating differentials to negative values. So if you have an element in the stable homotopy groups of spheres, you ask what element in the stable homotopy groups of spheres detects you in this spectral sequence, and that element is called the Mahal invariant of alpha. Okay.
Is it ever equal to the thing you started with?
Beyond, I think 1 or something, no. And so go away, take away the identity map, and in general you have this situation where the degree of the Hopf invariant of alpha is going to be something less than the degree of alpha. But the degree of the Mahal invariant of alpha is going to be bigger than the degree of alpha. Now, this also explains, given this spectral sequence, you might think that it's supplying you with yet another kind of Curtis algorithm inductive technique for computing stable homotopy groups. But you see, the key here is that you previously computed the lower homotopy groups that contain the Hopf invariants. Here, you can't. Here, it's like you're somehow future information is influencing where you're currently at. So there's no sort of way for using this to just sort of inductively compute stable homotopy groups of spheres.
Do you happen to know the Mahal invariance of the Hopf-2 eta nu sigma?
Thank you for saying that, because I was about to forget to tell you, and that's what I was supposed to do at this point in my talk. So the Mahal invariant of 2 is eta. The Mahal invariant of eta is nu. And the Mahal invariant of nu is, can anyone guess? Sigma. Oh, okay.
So are these detected in the atoms? I mean, how is the Mahal invariant related to operations in the atoms? Right? It looks like it must be.
I'll get to that. That's a very good question. Yeah. So I haven't even talked about the atom spectral sequence yet. So that's okay. I like the enthusiasm. So
What's the Mahal invariant of sigma?
Sigma squared. Yeah, in general, these get a little more mysterious. It would want to be the next Hopf invariant 1 map, but there aren't any. So it decides to instead start going to the Curvaire invariant elements for whatever reason. Okay. It's because it's not sick enough. Okay. So, okay. Now let me continue. So this was a bit of a digression, but it will come back to us later. So the EHP spectral sequence is not the ideal way to compute stable homotopy groups of spheres. If you don't care about the unstable homotopy groups of spheres, your best way to compute stable homotopy groups of spheres is using the atom spectral sequence. And so that's what I'm going to talk about next. So let's suppose that E is some nice ring spectrum, where I won't say what I mean by nice. Whatever nice means is nice enough so that the pair E star and E star E, so take pi star of E and E star of E itself, this pair forms a Hopf algebroid. What does this mean? It's basically a Hopf algebra. It means that this E star E is both an algebra over E star and it's a co-algebra over E star. And I'm actually just interested in the co-algebra structure. So what does it mean to be a co-algebra? Well, it means you have a co-multiplication map that goes from E star E to E star E tensor over E star. E star E, co-algebra. And then this is interesting because then the E homology of any spectrum gains the structure of a co-module over this co-algebra. This is co-module. And then the atom spectral sequence is a spectral sequence that starts with E homology and ends with homotopy. So the atom spectral, so there's one for every ring spectrum. So the E-based atom spectral sequence starts with an E2 term, which is equal to X of co-modules over E star E. And it converges to the homotopy groups of the spectrum X after you complete it in a suitable way with respect to the cohomology theory E. And this E nilpotent completion may or may not coincide with what's called the Bausfield E localization. Now, your most basic example is the case where E is equal to HFP, and then E star E is the dual Steenrod algebra, and this spectral sequence is just called the atom spectral sequence. It's the first instance, historically, it's the first instance of this spectral sequence. So this is a picture of the atom spectral sequence at the prime 2. So in this picture, what you'll see is the x-axis is the t minus s. So the columns of this spectral sequence read off the answer, similar to other pictures I've shown you, and then the s is this y-axis over here. Now in this spectral sequence, you see, so this is a computation. You can't see it here, but this is through roughly like dimension 45 or something like that. This spectral sequence has many differentials, and these differentials go back by 1 and up by r. Okay, so that's how these differentials work. Okay, so the Hopf invariant 1 elements have a very particular, play particularly nice with this spectral sequence. Let me try to make it so you guys can really see this. Okay, so here on the 1 line of this spectral sequence, all the Hopf invariant 1 elements are detected. So here's 2, here's eta, here's nu, here's sigma, and then this one isn't there because it supports a differential. So in general, you have an element of Hopf invariant 1 if and only if x is detected by this element on the 1 line. So the 1 line is generated by guys called hj, which don't show up here. But here's h0, h1, h2, h3, h4. You kind of see that little blob is supposed to be an h, detected by an element called hj in the atom spectral sequence on the 1 line. And so then the non-existence of the Hopf invariant 1 elements is a consequence of these HJs not being all permanent cycles. In fact, basically Adams's proof of the Hopf invariant 1 problem was more or less by this sort of the origin of this spectral sequence, by more or less showing that there's a differential on these HJs. That d2 of hj is equal to hj minus 1 squared times h0. For j bigger than or equals 4. So that's basically the Hopf invariant 1 theorem. Now another thing I'd like to highlight for you is how the image of j is seen in this spectral sequence. So here, the image of j now shows up, it hugs up against the 1/2 vanishing line of this spectral sequence and occasionally plunges down as far as it needs to. That's the image of j. Okay, now some other elements I'd love to tell you about are the Curvaire invariant 1 elements, and they're all detected on the 2 line of the spectral sequence. So these are, I've highlighted them in purple. These are the Curvaire invariant 1 elements. They're called theta j. So what is this Curvaire invariant? You hear about this Curvaire invariant, it makes you want to know what it is. So it's if you take the stable homotopy groups of spheres, Triagon showed that these things are the same thing as the framed cobordism groups, cobordism of framed manifolds. Now, one example of a manifold that admits a framing is an exotic sphere. And so let's let theta n of exotic n spheres, potentially exotic n spheres. So these are homotopy n spheres up to diffeomorphism. So you put different differentiable structures on the sphere, basically. And then, as I indicated, if you have an exotic sphere, you can then give it a framing, and then this will give you an element in the frame cobordism group. So this leads to a map from theta n to pi n s modulo the image of j. And if n, this was studied by Curvaire and Milner, if n is not congruent to 2 mod 4, then this map is surjective. So this says that every element of the stable homotopy groups of spheres is representable by an exotic sphere. That's kind of cool. But if n is congruent to 2 mod 4, there's an obstruction to making this happen. And that's called the Curvaire invariant. So there's a little exact sequence like this, where this is the Curvaire invariant. And so if an element has Curvaire invariant 1, then it is not representable by an exotic sphere. Well, then a theorem of Browder uh, 1969 says that X has Curvaire invariant 1 if and only if X is detected by Hj squared in the atom spectral sequence. So basically, what this says is now you're trying to show these guys Hj squareds are permanent cycles. And when you start to do these computations, they seem to all be permanent cycles. They're not supporting differentials. And so if you look at